Good afternoon. Today I want to report some recent work in PEXSI and did with Lin. They did some with this new algorithm to find the chemical potential more robustly in a PEXSI package now. So this is going to be my presentation. First, I will talk about PEXSI for the DFT, and then our current new algorithm to robust determination of the chemical potential, some parallelization and numerical results. So in the Convergence DFT, the most widely used algorithm, I think it is the direct diagonalization method, which you can calculate eigenvalues of the Hamiltonian matrix. However, there is another way of expanding the Fermi Dirac operator into some simple functions such as the Green's function or like rational approximations. The FOE method is trying to do that in a Green's function way, and we kind of expand the density matrix of a system into like 40 to 80 what we call poles, and then for each pole we can calculate the selective inversion of that system, and then we can add up to get the global density matrix of the system. So this kind of methods compared with the direct diagonalization methods, it is much I would say cheaper in terms of computational complexity. It is at most n square, and for the direct diagonalization methods, you kind of need to have n cube computational complexity, and this is going to be expensive for big systems, especially more than like 1,000 atoms. So it only scales up to like 5,000 CPU cores, and however, for the FOE methods, which we have a package called PEXSI, can scale up to tens of thousands of CPU cores. And this kind of FOE method can also be compared with linear scaling methods, being that the selective inversion method works for both metallic and semiconductor system, and it remains accurate at a low temperature. So we have a package called PEXSI. The PEXSI used a contour integral to expand the Fermi operator, and basically it used 40 to 80 poles in a real DFT calculation. And it scales up to thousands of CPU cores for a single pole. So it has two levels of parallelization. The first one is the embarrassing parallel over the poles. So you have 40 poles to embarrassing parallel over. And then for a single pole, you can parallel it using like NP row by NP column. So it's going to be like thousands of CPUs within a single pole. And it has been integrated into many DFT codes, and typically used for very big systems. One challenge in the current PEXSI evaluation is that we need to determine the chemical potential, because the FOE method doesn't calculate the eigenvalues of a system, so we cannot get the chemical potential directly from counting the eigenvalues. So we need to kind of have another way of getting the correct chemical potential. Recently, there is some work by Moussa, and he has proposed an optimized pole expansion method to expand using Zolotarov expansion for the sum functions through the numerical optimization. This method reduces the number of poles and to 10 to the 30 poles. However, this method, there are some drawbacks in this method. First is that it requires some extra work to computing the energy density matrix and the force density matrix, and it cannot achieve very high accuracy, such as 10 to the minus 9th heart rate per Bohr. This is, however, in real applications, we don't kind of need that very high accuracy, and I would say the Moussa's pole expansion method works very good in practice, and we kind of gonna make it default in our PEXSI 1.0 version. And also we are gonna put our current new robust chemical potential determination method into that PEXSI 1.0 version. So for Fermi Dirac distribution, these two pictures, the left one showing a semiconductor system and the right one showing a metallic system. So you can see the Fermi Dirac distribution of those two systems are quite different. And in the old PEXSI method, what we do is we are doing kind of a dissection method to search for the chemical potential mu. For example, if we have this X-ray being the searching range, and at first we need to calculate this middle point of this mu here, and then it being the lower bound, and then we are calculating the second point in here. So after several iterations, we cannot get the correct mu for this single SCF step. However, this is going to cost us because each PEXSI evaluation takes a lot of time, and we kind of want to use Newton's method to take the derivative information into account to accelerate this convergence. But this also have some problems. We need to set up some safeguard to ensure that the derivative doesn't give us a wrong answer to go out of this searching range. And this is kind of tricky in the real application, because the users will have to set up a parameter which is heuristically you don't know before you start the calculation. So you have to set up it blindly, and hopefully it will run and converge very good. However, we want to kind of find a new way to determine the chemical potential for the Fermi Dirac distribution. So we kind of want to do it in a SCF convergence way. So for each SCF step, we will keep the lower and upper bound of the mu mean and mu max. So we will have a lower bound mu mean, and we will have upper bound mu max. For example, if we still have this, taking this one for example, if we still have the x-axis being the searching range, and we will do a bisection, we will kind of evaluate a Fermi operator in here, and then we kind of have the searching range being from mu mean being here and mu max being here. Then we interpolate the chemical potential and the density matrix so that it gives the correct results. This being that the SCF converges, and then in each SCF we kind of narrows down the mu mean mu max range so that we will get a very good approximation of the mu. So for this kind of method, we will have only one PEXSI iteration in each SCF step, so we don't need to calculate several PEXSI iterations. And we will introduce a point parallelization into this Fermi operator, because as you can see, if we have multiple points in the searching range, then we will very quickly converge the mu mean and mu max to a very narrow range. And then we will scaling and interpolate the chemical potential, and there will be two levels of narrow down the chemical potential, upper and lower bounds. The first one is a cost level. We will use initial counting, and the second one is the fun level. We will use the Fermi operator evaluation. So for the cost level, we will do an initial counting of the Fermi Dirac function, and then we will use the infinity mu to evaluate the n beta mu, which is the real chemical potential we are using, because n n infinite mu can be used for, so that with a tuning parameter called tau beta, so that we can approximate that tau beta to that. We're using the current n beta mu as the n beta mu minus tau beta, and as the lower bound, and as the upper bound for mu minus tau beta, sorry, and as a lower bound for mu plus tau beta. In that way, we can do that. The PEXSI will both have the the initial counting is much cheaper than the selective inversion, because for the PEXSI evaluation, we will have to do the sparse matrix factorization and selective inversion. However, for the initial counting, we only need to do the RU decomposition. And also, since we kind of have a very large number of CPU calls, so we are having, for example, n point by n pole and n sparse CPU calls, so that we can do a point n pole initial counting. This gives us a lot of points on this searching on the searching range for for bigger mu min mu max gap, and then we can quickly converge to a very short range like tau. And this figure shows the initial counting steps of the PEXSI. First, we have a very big mu min mu max range, and then for each mu, we will calculate the lower and upper bound of the mu min mu max. We will select the part which the mu max is lower than the exact number of electrons, and a mu min is bigger than the number of electrons. So that this is the next step of the initial counting. This being the new mu min, and the green line being the new mu max. So for the second step, it goes on, and when the range cannot be further refined, we will stop the initial counting and goes into the fun level of the PEXSI evaluation. So for the fun level, we will do the real expansion of the Fermi operator. And in a single SCF step, we will launch n-point Fermi operator evaluations. Of course, n-point can be 1 and 2n. And we will update the mu min and mu max according to the calculated n beta mu g. So in each SCF step, we will narrow down the mu min and mu max range. So between two SCF steps, we will keep a rigorous lower and upper bound of the mu min and mu max by updating the searching interval with mu min plus beta delta, beta v min and mu max plus delta v max. So we will also do, because we only do one PEXSI iteration in the current robust version of PEXSI, so we need to do an interpolate of the chemical potential and density matrix, so that we get a correct chemical potential and density matrix. We found that doing just a linear interpolation is very good in practice, and because the interpolation procedure also gives us, it will shrink the interval by a factor of a point minus 1, the inverse of n point minus 1. So this is going to be the algorithm of SCF calculation for PEXSI. First, when the SCF is not converged, we will have a H matrix and an overlap matrix S. And then for the cost level, we will do the initial counting for n pole plus n pole by n points. And then we will evaluate the n infinities mu g for all the processors associated with μg. And then we construct the lower and upper bounds, and then narrow down the lower and upper bounds, update the searching interval. And then we will do a fun level of the PEXSI evaluation. For the fun level, we will do endpoints of PEXSI at the same time. And for each of this PEXSI evaluation, we will do, for all the poles, we will do the PEXSI, do a selected inversion and RU factorization. And then we will evaluate the mu, and also we will perform the linear interpolation for the mu and chemical potential and the density matrix. At the end of the SCF, we need to update the search interval with the difference of the potential, delta V.
Sorry, what's the delta V mean and delta V max?
So the minimum value of delta V and the maximum value of delta V. You have two potentials, and you use one potential to minus the other one, and get the differences.
So the reason is that if between the two SCFs, if the difference of the potential in the real space is denoted by delta V, let's say delta VR, then you can prove if mu min, mu max is a rigorous bound for the previous potential, then mu min plus delta V min and mu max plus delta V max must be a rigorous bound for the mu potential. So you can reuse the previous information, and you don't need to go back to the inertial counting step. So basically, the inertial counting sounds like there is iteration, but quickly it will be skipped.
So delta V mean usually is negative.
Delta V mean,
yes.
Not necessarily. It depends on how it's just it is what it is. But if you, let's say, normalize everything to be zero, you have a reference point, it's zero, yes, delta V mean could be negative, delta V max is positive.
And then we perform our test on actually 3 systems. The first 2 one are the PNR and graphene system for a semiconductor and metallic system for 180 atoms. And we also perform a 6,000 atom calculation for PEXSI using like 5,000 CPU calls for the timing, to compare the timing between the current algorithm and PEXSI before. So the tests are performed on an Edison NERSC with our code called KS-DFT package. So first, we would like to examine the pole expansion accuracy with Moussa's optimized pole and the contour integral pole expansion. So for the contour integral pole expansion, we can say that it achieves very good numerical results, with the delta E being 10 to the minus 7 and delta F being 10 to the minus 9. However, for the process expansion, we can achieve moderate good numerical results. But this, I would like to say that this is going to be enough in the real practice, because using just like 20 poles for Moussa's expansion. And since all the pole expansion is going to need less number of poles, using like just 20 poles to approximate 60 poles in contour integral. So we have saved a factor of 3 in the Moussa's expansion here. And we also compare the current SCF accuracy for those 2 systems with scalar pack and PEXSI, what we call PEXSI new is the current PEXSI, and PEXSI old being the old PEXSI. So we can see that we can all converge to 10 to the minus 7 for the SCF convergence for the potential residual error, and it kind of show the same convergence rate for the SCF. Also, one thing is that the current PEXSI timing, we don't need to do the PEXSI initial counting over and over again to restart. So the PEXSI initial counting is getting a lot of I mean, in each step, we are having like 2 to 3 steps of PEXSI initial counting for the current PEXSI. And for the old PEXSI, sometimes it takes up to 8 steps for the initial counting. And for the PEXSI evaluation, for the Fermi operator evaluation, we only need 1 Fermi operator evaluation in the SCF along the SCF iterations. However, for the old PEXSI, we need 2 to 3 PEXSI Fermi operator evaluation. And the right figure shows the timing for a 6,000 graphene system with this 3 is with 5,000 CPU calls, and this is a scalar pack timing, and we can see that PEXSI always outruns the scalar pack. And for there are 2 parts in PEXSI. Basically, the first part is the LU factorization, which is used, and another part is the selective inversion. Our tests show that the selective inversion actually scales very good if we use like a lot of poles, and because this is an embarrassing parallel, we can also say that the PEXSI new is actually a factor of 2 compared with the PEXSI old for the timing here. And since we are doing a convergence comparison, we want to note that the interpolation of the mu actually helps during the SCF iteration, because the mu max minus mu mean, which is the red line, is actually converging not so fast. However, for the mu minus mu converged, it actually converges very quickly to 10 to the minus 6 for this is the graphene 6,000 atom.
Do you know what the dips are?
Sometimes it goes up to the positive numbers, and sometimes it goes down to the negative numbers.
You mean the?
Basically, it's a coincidence. Fluctuating.
Okay. These are so pronounced, dips. I wonder if it corresponds to something that happens in the SCF iteration.
Yeah, we're done.
Yeah.
And also we do MD simulation for the semiconductor system, I think, and graphene. For the graphene system, and this is 180 atoms, and we can see that the new algorithm is quite stable in terms of the delta, the E-drift. E-drift being the current step of MD, the difference between the current energy and the initial energy to minus divided by the initial energy. So the conclusion is that we present a robust and efficient algorithm that can determine the chemical potential in PEXSI for solving the KS-DFT, and it dynamically update the lower and upper bound for the chemical potential. So we have implemented this method in the PEXSI 1.0 version, and this is going to be like a factor of 2 in terms of speed up for a very big system like graphene 6,000. And we have a new point parallelization in the PEXSI 1.0, and we will use Moussa's optimized pole expansion set as default in PEXSI 1.0. And for acknowledgement, we thank the NSF, SADC, and NERSC. Thank you.
Do we have any questions? Volker?
So the scalar pack benchmark numbers, which scalar pack Was that, so was the scaling pack, was it a vendor implementation? How does it scale? So you compared against scaling pack somewhere.
Yes, vendor in the sense of NERSC, PDSY, EVD. So that's the best one.
So that's creative side.
Yeah. So
But does it still scale out there?
the scales to around 4,000, 5,000, around 4,000 core-ish.
In principle, so the scaling pack, our experiences with alpha were that it's tricky to compare against most implementations called scaling pack. So as in the original scaling pack is usually that we use it some vendor implementation or vendor version. But anyway, so scaling pack goes up quite
That's right.
drastically.
Yeah. We can.
No longer scales. So comparing against scaling pack is difficult because you don't know which range you're in originally.
Right. Yeah. We can add an extra column now that the DG is interfaced with ELSI. Just turn on the alpha version and see how it works. Yeah. We can just add another column.
Any other questions? Okay, and with that, I think we can call this session to a close. So thank the speaker again.